Hi, I'm Sagie, CTO at Cloudigo. I'm also one of the creators of two official OpenStack projects, Project Dragonflow and Project Courier. I'm very proud to see that both of them have been presented today. I'm presenting with Eyal Cohen, director at Silicom, and we have a quite interesting topic today to speak about. We are going to speak about next generation trends in data center network and OpenStack network in specific. This is coming from feedback that we received during the last year from customers, vendors, and users alike. So the first topic is SDN, and I could potentially speak the entire session about SDN. There are, for Neutron, if you take, for example, OpenStack networking API, you have around 60 different drivers and implementation. There are a lot of SDN solutions out there, which are varying with how they solve the problem. But if you look at all of these solutions, then they all concentrate on overlay, meaning they are enabling network virtualization. Essentially, they take your physical network, if it's layer 2, if it's layer 3, and allowing tenants and users to deploy their own networks on top of this physical network. But when we are thinking about what SDN was all about, it was also about the underlay, being able to program your physical network, being able to determine the traffic path between an application sitting at one server to an application at another server. And what we see is that with current topologies, and the most common physical topology today is leaf spine, this is blocking us, especially when things are oversubscribed. And what we see is that users are actually experimenting and researching new kind of topologies, a new kind of connectivity. And just as a nice exercise, I urge you to look at TensorFlow, Google TensorFlow. It's their deep learning cluster. They publish some photos from internally in their data center. It's very interesting how they do things. Another trend, and this is actually, it's already a fact, but it's only increasing, is that east-west traffic, meaning traffic inside the data center between servers internally in the data center, is the majority of the traffic, around 70 to 80%, and this is only increasing with the move to microservices. And again, the topologies today, especially when they are oversubscribed, are not fitting to such traffic. Another big trend today that is not directly related to networking is serverless. Anyone heard about serverless? Okay. So one major example for this is Amazon Lambda. And essentially what serverless lets you is to define processing code, define a set of triggers, and upload it to your cloud or your infrastructure. And then you don't need any VM or container or any containing part that will run this processing. The infrastructure is in charge of running this code where it sees it best. It puts the data in the center. And it has some few advantages. It removes a lot of layers and overhead from the development, and it speeds up the development process. When we look at networking, the networking is transitioning very, very similar to serverless. We started with hardware appliances, where the software there was highly coupled, highly bundled together. And then came NFV, and all the vendors ran and took their highly bundled and highly coupled software and just put it inside a VM. And what we see in the last year, and this is actually something that was surprising, we see even big vendors that are actually throwing what they have, or not throwing, but starting new initiatives to take their code and re-architect and rebuild their network services in such a way that fit microservices. And this is not very easy task because networking is mostly about state, synchronizing state, and microservices doesn't really fit to this. But what we see is actually that the next step is where the NICs and the hardware becoming smarter and smarter, then we'll actually be able to run some of these functions on the NICs and on the hardware. And since we have this hardware everywhere in our data center, we will be able to apply these services on the data everywhere. And this resembles a lot serverless. And in this regards, there are a lot of advantages that are usually cited when people are moving to serverless, automation, fast development cycle. But in the end of the day, if you can run 10x tasks in one server more than you can run today, then this is a very big business motivation to go. Another trend is the term network services. When I'm saying network services, I'm sure most of you thinking about routing, security, load balancing, NAT, and so on. What we see is that this term is actually expanding. There are a lot of recurring traffic patterns today happening in the data center, and we are going to see more and more services that actually leverage the infrastructure and leverage the network in order to create new kind of services. Some example could be messaging, publish subscribe, internal database cache layers, and so on. So we believe this term is going to be expanding and meaning much more. A common thing about networking is called shared fate, where you upgrade a version for networking equipment, you upgrade it and you pray, and if something breaks or if there is some problem, then you can potentially break your entire network, and hence the shared fate. We see a lot of work today in being able to slice your network, partition your network, allowing rolling updates to networking software, being able to steer some percentage of the traffic from your main network to an experimental network. And there are few projects that are coming to life in that. For example, if you heard about IST.io coming with Kubernetes, and so on. And what all of this is enabling are new kinds of routing and new kinds of networking paradigms inside the data center of how we steer traffic. We believe that there is going to be, and it's already being shown in few projects, that the application is going to come closer to the network. We are going to see routing that is layer 7 or applicative aware. And even looking a bit further, we are going to see machine learning and AI in routing and networking. Today, just like you can take your PC and install any kind of operating system, Linux, Windows, or whatever in it, you can buy a networking switch from a hardware vendor, relatively cheap, and install a networking operating system from another vendor. There are a variety of these projects, starting from open source, semi-open source, and proprietary. Many of these solutions are already relatively mature and been in production for a few years now. And usually when I'm talking with people about this disaggregation, then the advantage they talk about are price, which to me is debateful, and avoiding vendor locking. But what we actually see, which is also interesting, is that a lot of users are taking this for being able to customize your network. If you are already building a data center, if you're a cloud provider, if you're a service provider that doesn't use a public cloud or wants to build your own data center, then you want to use this fact in order to gain business advantage. And the way to gain this advantage is by essentially making the network fit very well to to the workloads or the applications that you are planning to run on it. So being able to customize, to reduce layers or features that are not needed in networking equipment and move faster are a very big motivation, and is essentially what we believe will make this disaggregation grow. In essence, what we see, and all of the trends that I talk about until now lead to this point, and this is that the NIC is becoming the most important point in the data center. It's becoming the key, the edge king. It what connects between the virtual and the physical network. And surprisingly, we get this feedback even from very large switching and companies that are understanding this fact and are pursuing new business opportunities in this area. The NICs are becoming smarter, they are becoming programmable, they are becoming embedded with FPGAs or with computation engine. And just for an example, you can look at Amazon. You would be surprised and how much Amazon is buying a switch today in their data center. And they are essentially not using any feature at all. They are keeping it very simple and moving a lot of the logic to their NICs. One such NIC that is already relatively mature and is addressing some of these trends that I talked about is Intel Red Rock Canyon. And I'll hand over the talk to Eyal now to speak about how this NIC can solve a lot of the challenges in data path processing today.
Thank you, Gal. Great insights. Yes, we will try to check why was the NIC coronated to be the next king for the data plane solution. And we will do that by examining, briefly examining common software-based data planes, and we'll try to see what's good with them and what's less good about them, and how the NIC can handle whatever it takes to handle in order to operate better the network and serve better the overall workloads. So my name is Eyal Cohen, and I'm from Silicom. Silicom is a NIC manufacturer. We're tightly coupled with Intel. We're Intel network builders, and I'll start with a question just to get the feeling of how many people here ever dealt with NIC programming, like filtering engines or SRIVs? Few. Okay. So what is important about data planes in general, and specifically with orchestrated environments? First of all, of course, bandwidth. And packet rate. So if a data plane is committed to uphold like 10 gigabit of traffic, then it should sustain 10 gigabit of traffic without any packet loss. Same goes for 40 gigabit traffic, right? You do 40 gigabit traffic, do it right, do it without any packet loss. So bandwidth is one thing, and bandwidth should be sustainable and constant, right? I mean, we don't want to have any impact on bandwidth coming from unknown directions. Another thing about network integrity, of course, is latency. I remember Eyal Cohen from Mellanox in his great discussion before, and was mentioning also the latency. And the latency should be, first of all, as low as possible, right? And second of all, any guesses? Exactly, constant. Constant and predictable and deterministic, exactly. And why is that? And why is that? Because we would like to know, if in case of troubleshooting, we would like to know that network is predictable. And if we need to troubleshoot something, then we don't want to go to the network guys and say something wrong with your network, and they would say, oh, nothing is wrong with ours. Go to the application guys. And the application guys would say, we're not receiving any packets. So once we have a stable and consistent network, then we have a better chance to have an overall more stable environment. So I will touch base on several software-based data planes, and we'll see what's good in them and what's less good in them, and then I will try to gather all the threads together and see how hardware performance, hardware acceleration, or hardware offload can give us a really good added value. So first of all, let's talk about OVS. We're mentioning OVS a lot in these discussions, and we like OVS because it's a flow-based data plane. It's easy to use. It talks flows, and we can program it quite easily. And it's good for virtualization because it supports VirtIO. It enables all the good features of live migration, pause and resume for VMs. But then again, it's quite awkward software engineering piece of machinery, right? Because it has kernel space and user space, and the interface between the kernel space and user space is not that efficient, and it features quite significant latency at times, and specifically when we are dealing with a lot of VMs, then things are getting heavier and slower by the VM. Another VM comes in, things are getting much more, much less efficient. By the way, I take questions during the conversation. This one goes for me. The hardware will go to Gal probably. Gal will be back, by the way. So let me just get, yeah. So that was about OVS. Huh? Okay, so one step ahead with OVS is the DPDK OVS. A DPDK interface into the OVS gets rid of the fact that the kernel mechanism or kernel driver is part of the data path, and it gives us better scale with multiple cores. However, by bypassing the kernel, we lose all the goodies that the kernel can provide us, such as IP tables for security groups, and even though we gain quite good bandwidth, the latency never decreases because DPDK mechanism is not the best in latency. Another common project is the VPP. VPP is a big one big user space main loop that comes from a different angle, and the philosophy in VPP is that packets are processed not packet by packet, but rather blocks of packets, one after the other, and that way, using some sort of a graph, the idea is to utilize the cache mechanism of the general purpose CPU. So it's a kind of a software mechanism that utilizes best the CPU for forwarding and data plane purposes. The thing is that it doesn't scale well. That's the truth. It scales up to a point, and then things are going south. And once we are at it, it's very hard to accelerate it or to offload some of the features down to a hardware, because on the first place, this data plane was designed to use to run best on standard CPU. Questions up until now? Okay. So, SRIV, Thunder. This is a kind of a mechanism that is implemented by the PCI. It's essentially a PCI tunneling mechanism that it used to multiplex or seemingly multiplex hardware up to the host, so the host would believe that there are several instances of the same hardware running on the same time. The good thing about SRIV is that it's very fast. It's very fast. It's fast. It's in terms of bandwidth, it's only limited by the bus bandwidth, by the PCIe, and the latency is quite good. However, it ties us very tightly to the hardware, and we lose some of the functionalities of the virtualization if we indeed would like to use virtualization, because it wouldn't use VirtIO on the first place as a front-end interface up to the virtualization, up to the host. So it gives us some sort of a limitation that we need to find a way to overcome. So Gal mentioned the FM10K, or the Red Canyon from Intel, coming from Intel. This is a controller that essentially is a combination of a real switch mechanism with a MAC interface to a host. And as a switch mechanism, it has the capabilities of a fully fledged switch, along with a rule engine and filtering engine, and a very impressive port density. I mean, with one controller, we can offer 2 external ports, even 6, and up to 24 external ports, with one PCA adapter that goes into a server. Essentially, and we will see it later on, it would enable us to get rid of the external top-of-the-rack switch, or at least not to rely on the top-of-the-rack switch in terms of advanced features of the networking, and we wouldn't be limited to the limitation of the top-of-the-rack switch if we were to use this kind of port density. So it's a real Mac, and it enables us to use SRIV without ever losing capabilities of switching and forwarding that we are losing if we're using SRIV with a simple NIC. And of course, we can combine SRIV interface with standard interface as we see fit. The nice thing to have a switch on a card that has 2 legs up to the host and up to 24 legs downstream is that we can really utilize the data plane on it in various ways. We can filter traffic coming up to a host. We can take traffic coming up to the NIC and send it onward to the network, and we can even do filtering stuff. We can decap and incap VXLAN. We can handle VLAN, and we essentially can take all those tasks off the host and put it down on the hardware, which was initially meant to do that. And if we will be smart, and Gal and his team were smart, and we will see what is the best thing to take from the host down to the hardware. That way we would achieve the best way to utilize the hardware to accelerate to accelerate the networking without ever requiring further burden on the host, relieving the host to do further processing and being able to gain decent and good and stable bandwidth and latency. So at this point, I will let Gal move on and describe the solution.
Okay, so again, essentially, we are a little bit out of time, so I'll just say, and Claudio was mentioned before, the way that we are doing is we treating networking and networking functions in a bit different way, and being able to provide a new kind of solution for data centers and infrastructure. Since we're out of time, if anyone is interested, please come and talk with us after this talk. And I was also told that I was putting you late for the break, so there is a break right now. So thank you, everyone.